This problem is a classic one where we have a bar hanging under the influence of gravity, and we're trying to figure out what the displacement or deformation of this bar might be. And we're going to use this newly found relationship between an internal force and this displacement, which is given by delta is equal to integral of p over EA with respect to x. Remember that p is just a function of x. This is not p times x here. And if you'd like to see the derivation, you can look at the video from fall 2024 for session 7. So we're going to think about equilibrium in connection with this constitutive relationship, which is really an extension of Hooke's law relating a displacement to a load through some material properties. So for the equilibrium portion, we first focus on using external equilibrium, and we can just draw this bar hanging from the ceiling. And we know that there's going to be a reaction force from the wall on the bar, and gravity is acting on the bar. So we can calculate out what the reaction force is by this balance of the reaction force and mg. And then we'll use this relationship that we've also talked about in class a little bit, where we can think of m as being volume times density. So that's the density, and this is volume, LA, so the length times the cross-sectional area. And we're going to multiply that by the g, as we see here. For internal equilibrium, we can write another, or we can draw another diagram which has a slice. And for this, we have a reaction force that we had here, and we also have a internal force P, okay, where the slice is. And we'll define an X and we'll define a G. But something is missing here. What's missing? We're missing the distributed force due to gravity. So let's just draw the little f here. And this little f has to be integrated through this length x. Okay, so now we're saying that x is defining the length until we get to the slice. And that means that a large force that is the culmination, well, maybe not culmination, but accumulation or the integration of this distributed force can be given as the following, going from 0 to x time of f with respect to x. And if we substitute in an expression for f, we get the following. Now, this expression might be a little bit confusing. Remember that the units for distributed force, and we talked about this in the class notes, the distributed force has units of force per length, or in many cases we might write it out as newtons per meter. And if we look back over here, we have an expression for force, which is rho, or density, times volume times g. So we need some type of force, and we need it per unit length. Well, the per unit length is going to be describing what's happening in this vertical direction. And so we just take out that length, and we now have a rho GA, right? So this is the same expression, just dividing by this length L. And you can kind of think of it, okay, that's what I've got. That's the contribution for a given cross-sectional area. And if I just make a little bit of height change there, I get a little dx. Okay, so this rho GA dx is going to be like that incremental amount of force that happens from essentially a slice along this bar. And so I need to integrate it up from 0 to the specified length where I took the slice. We do this integral, and it's kind of trivial. It's just going to be rho GA x, and then I plug in x, so I get rho GA x. So this describes the force from the distributed load and is acting externally on the system. So we have two external loads, R and this big F, and we have one internal load, and they're going to be in equilibrium with each other. So the summation of the forces in the x direction is equal to 0, and we can say that this P plus this F, or this F, okay, which is acting downward in the positive x direction, minus R, which is acting in the minus x direction, or R is acting in the minus x direction, is going to be equal to 0. So we now have P equals R minus F. And we're getting closer. We can plug in R, and we can plug in F, and we get the following, rho g8 times quantity L minus X. And this is a nice expression that we can then use with our constitutive relationship that we wrote out at the beginning. Remember, this is kind of like pli, but now it's an integral form of it. We can write out that the delta is going to be equal to taking out, if E and A are constant, then we just pull them out here. 1 over EA and going from 0 to L. Okay, we didn't specify that here, but we're specifying that here. That's the length, obviously, of the bar. Rho GA times quantity L minus X. This is here with respect to X. And we go ahead and perform this integral, and we then substitute in L and 0 appropriately. And the final result is rho G L squared over 2E. And this result is kind of a classic one and allows us to think about how gravity is, a constant gravity is pulling on a bar to get it to extend as it hangs. So let's go ahead and plug in some numbers here. We'll go ahead and we'll just do it in Colab because, I don't know, you've now got a lot of experience doing it in Google, and I think that Colab is quite useful. So we'll do import numpy as MP, and we'll go ahead and write out some parameters. So we have a rho, which was given as 2689 kilograms per meter cubed. So we'll just, whoops, it's even there. Wow, okay, it might maybe remembered, I don't know. Because it's a unique number, I guess. It's been a while though since I've run this in Colab. So 2689 kilograms per meter cubed. G, what did we specify? No, but we can just use 9.8. Oops. Okay, well okay, I had used I guess something else before 9.81. It's fine. L is given as let's see, 14.9 meters, okay? And E is given as 70 gigapascals. Okay. Now notice, the problem did give us the cross-sectional area of 7 centimeters squared. But if you look at our derivation of this relationship, the areas end up canceling out. Well, okay, I'm pointing, okay, this is the area here, but the areas here, the one in the denominator and the one in the numerator, those cancel out. So we actually do not have dependence on the cross-sectional area. So if it's a constant cross-section for a hanging bar, we're going to get the same result for the displacement or the deformation of the bar. So now let's write out that delta is going to be equal to rho times G times L. Remember, oh, here we go. L is going to be L squared. Oh, it even remembered. That's nice. But I don't really want to do E times 1 e to the 9. So I'll go ahead and because I already did it times 1 e to the 9. So I can just leave it like, well, I can't quite leave it like that. I need to put a parentheses because it's 2 times E, or I had to do 1/2 at the beginning. And either way, anyway, so now we'll do delta is equal to MP round, okay, and we'll do delta. What does it specify units here? It's in microns, so we'll go ahead and do it in microns. So we'll do times 1e6. Let's do like 3 decimal places, and we'll say that this is going to be units in of microns or micrometers, all right? Or micrometers. I guess the micrometer is the thing that you use to measure the length. And what do we get? We get about 42 microns using these numbers. Okay, well, I hope you found this example helpful. And if you have any questions, please feel free to take a look through the notes or talk to me in class. Thanks.